What is molecular replacement?
Molecular replacement makes use of already established structures to aid interpretation of an electron density map. It requires at least 20% of structure similarity to be classified as homologous. Molecular replacement is a method of solving the phase problem in X-ray crystallography.
The term phase problem denotes the loss of information concerning the phase of light when making physical measurements. In order to determine a structure from diffraction data, the phase problem has to be solved. This problem is not unique to X-ray crystallography only, but rather also arises in imaging and signal processing.
Molecular replacement relies upon the existence of a previously solved protein structure which is homologous to our unknown, from which the diffraction data is derived.
What do we want?
Superimposable protein models.
When do we want them?
Now. Why do we use it?
There's no Romeo without Juliet.
And there's no Fourier transform without phase information.
Molecular replacement provides initial estimates of the phases of the new structure from a previously known structure.
Software is used to account for any differences in orientation or crystal structure. The phase data for the known protein is applied to the diffraction data for the unknown. Proteins are refined until the two models become superimposable.
Here you can see the probe molecule with known properties and the target molecule. In the molecular replacement theory, the probe is superimposed onto the target molecule via rotation and translation. The phase can then be calculated and the Fourier transform performed.
This is a simple example which demonstrates the importance of information carried by phases. First, we combine the Fourier transform of the duck's amplitude with the Fourier transform of the cat's phases.
Then we reverse the Fourier transformation on the resulting mixture to reveal an image that is much closer to the cat than to the duck. This shows the relative importance of the information carried in phases to image interpretation.
Once the basic model is created, it is refined so that the observed model looks as close as possible to the model expected from the given dataset. Refinement can be defined as the optimization of a function of observations by changing the parameters of a model.
The degree of refinement directly reflects data resolution, and therefore a highly refined model is obtained from a dataset of high resolution. Data with low resolution can be improved using computer programs which study the model and add appropriate chemical restraints, thereby increasing the resolution.
What can we do once molecular replacement is used?
Each potential solution is subjected to rigid body refinement, and then the solutions are pruned to remove any that are equivalent after considering crystallographic symmetry and possible changes of origin.